Okay, so we will start the class, okay? So once again, good evening everyone. Is my screen visible? Is my screen visible? Hello?
Yes, sir.
Yeah. Screen visible, right? Okay. So in the last week, we have actually started with the deflection of beams, and we actually seen a brief intro on deflection of beams, right? So in today's class, we will see about the deflection of simply supported beams under various loading conditions. Okay. So is there a question in the chat box or yeah, fine. Okay, so today we are going to see about the deflection of beams or for deflection of like simply supported beams, cantilever beams under various loading conditions. Okay, so first we will see about the simply supported beam with constant point load. Okay, simply supported beam with a constant point load. So you have been given a beam like this. Okay, this is a simply supported beam, and you are having a point load at its center. Okay, so can you say where will be the maximum deflection will happen and where will be the maximum slope that will happen? Say for example, let's say this as point A, B, C, and whether this is whether can you draw the shear force diagram and bending moment diagram, and can you say whether this is a case of pure bending or not? Sorry, someone has unmuted their voice. So could you please mute? Yeah. So can you say whether this is a case of pure bending or whether this is not a case of pure bending? Sorry, can you please Silver Raghavan? Yeah, thank you. Excuse me, Silver Raghavan, can you please unmute yourself?
Sir, I think I didn't hear you.
Yeah, oh, 1 minute, sorry. Silver Raghavan, can you please unmute yourself?
You can mute him by yourself.
Yeah, okay, fine. Yeah. Mute Silver Raghavan for everyone in the call. Yeah, now it is fine, right?
Yes, sir.
Yeah. Yes, can you say for this given loading, like whether this is a case of pure bending or not? What is the need for pure bending? Or what is the condition for pure bending? Can you draw the SFD and BMD?
Yes, sir.
Yeah.
Two rectangles.
Yes, it will be two rectangles like this. Okay. And what is the BMD?
Parabola.
Parabola? Are you sure?
sorry, sir, straight line with
Straight line. Yeah,
maximum at center.
maximum at its center. So whether this is a case of pure bending or
No.
the, yes, because in the case of pure bending, like you should have a constant bending moment, okay, all through the beam. For example, the bending moment diagram should look like this. Okay, for example, this, let's say this is a moment of value m. Okay, so all through the length of the beam, the bending moment should not change across the length of the beam. Okay, so this is, we term it as pure bending. So in the case of pure bending, what will happen? The what will happen to the radius of curvature? It will be like,
Constant.
yeah, it will be like a circular arc. Yeah, constant means it is like a circular arc. Okay, so here the bending moment value is something like this. I mean, bending moment diagram is something like this. Okay, with the maximum at its center, and its whose value is, anyone?
Or W L by 2. L by 4.
Yeah, it is WL by 4. Okay. So for simply supported beam with a constant point load, like you will be having, where can you actually see the maximum deflection and where can you actually see the maximum slope? Anyone?
At center, maximum deflection.
Yes. So you will always get the deflection maximum at midspan. Okay. So this is known as the midspan. So deflection is maximum at the midspan. Okay. Whereas where is slope maximum?
Extreme ends.
Yes, it is maximum at the supports. Okay. And slope is maximum at the supports. So this is true for any kind of simply supported beam where the loading is kind of symmetrical. Okay, symmetrical in the sense like the load values should be equal, and also it should be spaced equidistant from the either support. I mean either side of the supports. Okay, for example, like for a symmetrical loading, I could give you another example where the deflection is maximum at its midspan. Okay, and also the slope is maximum at the supports. For example, like let's say I am having a load like this of W, and let's say I am having another load like this of W. So here you can see it is L by 2, L by 2 distance, L by 2 distance, L by 2 distance. Okay. So this is an example of simply symmetrical loading. Okay. So for this case also the deflection is maximum at its midspan. Okay. Y is maximum here. For example, if you draw the deflection curve, it would be something like this. Okay. Where the deflection is maximum at its midspan. And whereas if you draw the slope, like it will be something like this. Okay, and how to measure the slope? It is like kind of an acute angle. Okay, so like this I will be measuring the slope, and we have already discussed the sign convention, right? Can anyone say the sign convention for slope?
For clockwise, negative.
Yes, so for clockwise it is negative and for anti-clockwise it is positive. Okay, so this is the case of symmetrical loading for a simply supported beam. Let's take another example for the same symmetrical beam, I mean simply supported beam. Okay, with a load, let's say here. Okay, and the distance is like L by 4, and this is 3L by 4. So here what can you say about the deflection? Here where will theta max will be located, and where like you can see the maximum value of deflection. Let's say like this is the midspan. So here in this case, this is a example for unsymmetrical loading. Okay, so here you can, when you draw the deflection curve, it will look something like this. Okay, so you can see the deflection to be maximum at its like in this region. In this region, you will say like the in between this region you will have maximum deflection. Okay, and where like the load is near to the support which is near to the load. Okay, here there you will be getting the maximum slope. Theta is maximum since you are having the load which is near to the support A. So here you can say the theta will be maximum. Okay, is it clear for unsymmetrical loading in which region you will get maximum deflection and in which region you will get maximum slope? Yeah. Shall we proceed to the next problem?
Yes, sir.
Yeah. So now you are all having access to that formula sheet which I have attached, right?
Yes, sir.
Okay, fine. So now let's derive the slope and deflection equation for case of pure bending. Okay, and then we will proceed to the problems. Okay, so for pure bending, okay, someone having a question in the chat box?
Hello.
Yeah.
Actually, that formula sheet, how to access that? Could you please tell me?
Okay, actually I've shared it in the Google Drive. Wait, maybe I
I'll
will
share
do
it,
it.
sir.
Yeah, thank you. You have shared it, right?
Uh,
Sharing it, sir. 1 minute.
Yeah, sure. So this is again a simply supported beam. Okay, and at the ends I'm having a bending moment. Okay, so when you draw the BMD, it will be something like this, right? It will be a rectangle. Yeah, agree or not?
Yes, sir.
Yes. So here we have to. Can you say where will be the y max and where will be the slope value will be maximum and where deflection will be maximum for this case?
At center, delta max
Okay. Yeah.
and slope max at ends.
Yes. So at the supports, like the slope will be maximum, whereas at the midspan the deflection will be maximum. Okay, and the slope at the midspan it will be 0. Okay. So this is the deflection curve which I am drawing here. Okay. So this will be theta or theta max, and this will be theta max. Okay, this thing is theta max, and here this is the deflection curve. Okay, so somewhere at this point maybe it could have its center of curvature. Okay, and this point is the total radius of curvature. Let's say this as point O. Okay, and this is the total radius. Okay, this is R, and this is also R. Okay, up to this it is clear, right, what I have done? And let's say this length is L by 2 and this length is L by 2. Okay, so can you say what is this angle will be? So what we are going to find here is what is the expression of theta max and what is the expression of y max. We are going to derive for this pure bending case. Okay. The rest of the cases we will be having basic formulas which I have shared with you in the Google Drive. Okay. So can you say what is this angle? In terms of theta you can say, okay, this is theta max, okay, or which we can assume here this as theta. Okay. So what can you say about this angle?
Is it dy by
Cos
dx?
theta is equal.
No. In terms of angle, you can say, like for example, whether it will be theta or whether it will be 180 minus theta or whether it will be 90 minus theta, something like that. I need that kind of an expression.
It is 180 minus theta.
180 minus theta, no. See, for example, this is the curve, right? And this is its radius, okay? So when I draw a tangent, okay, what will be this total degree value?
90.
90. Okay. And what is this angle alone? For example, what is this angle alone?
Theta max.
Yeah. So theta I have denoted it as theta. Okay. So this total angle is 90 degree and this small angle is theta. So what will be this angle?
90 minus theta.
Yes. So it will be 90 minus theta. So this is okay, right? How I have got this 90 minus theta, or should I have to explain it again? Come on, if the session would be interactive, then we can solve more questions. Okay.
No, it's
Because
understandable.
yeah, so I need some kind of feedback so that like we can proceed very fast. Okay. Yeah. So this is 90 minus theta. Okay. And then when we draw the, for example, we need the expression of this theta, right? So I am isolating this triangle and then I am looking at this is the value of y which I want. Okay. This is y. And
So
this, yeah,
is this triangle OAB?
yes, it is triangle OAB and this is 90 minus theta. So now I want sine of, I mean, sorry, cos theta. What is cos theta actually? Cos of 90 minus theta.
L by 2 by R.
Yeah, it will be L by 2 by R, which means like L by 2R. And here I can write this as sine of theta, right? Which is equals to L by 2R. And then for small angles, we can write approximately sine theta as theta, right? So theta will be equal to L by 2R. Yes? Up to this, it is clear?
Yes, sir.
Yeah. So then, how can I replace this in terms of the bending moment?
I didn't get it.
Yes?
Didn't get it in terms of.
Okay. This triangle you cannot understand. Okay. See, for
Yeah,
example,
I understood the triangle part, but didn't get your questions.
okay, sorry. So see, we have written theta is equals to L by 2R. Okay. So I need this same equation because since I cannot easily find the value of R, I need the same expression in terms of bending moment M. So how can I replace R in terms of bending moment M?
1 by r is equal to m by ei.
Yes, good. 1 by R is equals to M by EI. So from this, I can replace this, right? So the final expression will be ML by 2EI. Okay. So you can also cross check this with the formula sheet which I have attached in the Google Drive. Okay. So now coming to find the Y max expression. Okay. This is Y max. So how can I find y max? Any idea? Can I use Pythagoras theorem? And if so, where can I use Pythagoras theorem?
Sir,
Oh,
yes, sir.
yeah. Okay. So OA square. See, I am taking this same triangle again. Okay. So it will be OA square, which is the hypotenuse, is equals to OB square plus AB square, right?
Yes, sir.
Yeah. So what is the value of OB square?
R minus Y max.
Yes, it is R minus Y max. Okay. The whole square plus what is the value of AB square? It is L by 2, the whole square. Okay. And what is the value of OA? It will be R square. And if I'm elongating this term, it will be R square is equals to R square plus Y max square minus 2R Y max plus L by 2, I mean L by L square by 4. Okay. Yeah. So actually y will be a very small value, okay, in terms of like 0.01 mm or 0.1 mm, something like that, okay. Y is a very small value. So we can actually neglect y square, okay. So neglecting this component. So the final term will be r square is equal to r square minus 2 ry max plus L square by 4, okay. So again from this, what is the final expression I will be getting for y max? It is L square divided by 8r. Again, when I am replacing this in terms of m by ei, it will be ml square divided by 8ei. Up to this, it is understood, right?
Yes, sir.
Yeah. So from this, what can you infer from theta is like theta is directly proportional to the length of the beam, okay, and y is directly proportional to square of the length of the beam. Okay, so y is actually one order higher than theta. Okay, so this will be the same situation for all types of beams. Okay, for example, in theta, if you are getting like L square, then y max, I mean, the value of the deflection will be L cube, something like that. Okay, and also the other inference you can get is like theta max as well as y max is inversely proportional to 1 by ei, okay, which is the flexural rigidity of the beam, okay. So if if ei is greater than y max or the theta max will be a very less value, okay. So for designing of beams, when you are having the combined value of ei as very high value, then you can actually reduce the deflection and slope, okay. So up to this it is clear, right?
Yes, sir.
Yeah. So from this, what I can write is like, see, I am actually going to generalize. In presence of concentrated moments, theta max is equals to 1 by C1 ml by EI, okay, and Y max is equals to, where C1 is constant, C1 and C2 are constant, okay, m L square divided by EI, okay. And similarly, in presence of concentrated loads, this you can cross check with your formula sheet also, okay. Concentrated point loads W, theta max is actually 1 by C1 W L square divided by EI, and Y max will be 1 by C2 W L cube divided by EI, okay. And in presence of distributed loads, okay. distributed loads, which is in this case I am denoting this distributed load as small w. Okay, small w is like 10 kilonewton per meter, something like that. Okay, so in case of distributed loads, theta max will be 1 by c1 w L cube divided by EI. Okay, this W is small w. Okay, and Y max will be 1 by C2 W L power 4 divided by EI. Okay,
Hello.
yes.
So the in presence of concentrated point load means is it at center only or formula applicable for any point?
No, see, actually, this formula, for example, WL square, this L square doesn't change for any kind of beam with concentrated point loads. Okay, but this 1 by C1 value actually changes for different kinds of loading, even for a point load. For example, if I have like this, okay, a simply supported beam, okay, with a point load at its midspan, then you will be having what is the value of Y max which I have given in the formula sheet? It is okay. I didn't have my formula sheet ready.
WL cube by 48 Ti.
Yeah, thank you. So it will be WL cube divided by 48 EA. Whereas for example, for a different cross section, if you can take, okay, at any different length, then this 1 by 48 will actually change. Okay,
Okay.
yeah, the constant value will actually change. Is it fine?
Yes, sir.
Yeah. So in general, I'm saying, for example, when you have a standard loading, okay, standard loading in the case of like where the formulas are readily available, there you can see these type of variations. So like it is very much easier to remember the formulas. Okay. So that's the thing I have said, like for distributed loads, you can remember like this. Only the constant value changes. For point loads, you can easily remember like this. Okay. So I am proceeding to the problems. Okay, so before that there is one small thing. Okay, so this is a cantilever beam. Let's say here I am having a load at a distance of L by 2. Okay, this has point A, B, C and D, and at point C I am having a bending moment like this of WL. Okay, can you draw the shear force diagram and bending moment diagram? This length is again, sorry, this length is again L by 2 and this length is L by 2. How does its SFD look like?
Rectangle for AB portion.
Yes, it is a rectangle for AB portion and it is negative. Okay, and for BC and CD portion,
Nothing.
yeah, it is 0. Okay, so from this you can draw the bending moment diagram. What will be the variation of bending moment diagram from A to B, and what will be the variation of bending moment diagram from B to C and C to D?
A to be linear.
Yeah, 1 minute.
WL by 2.
WL by 2, the magnitude of bending moment at A, it will be how much? It is WL by 2 or
WL.
it should be, see, for example, this moment is of value WL, right? So what will be the reaction moment at point A?
WL plus WL by 2.
Yes, so it will be 3WL by 2. Okay? Is
Yes,
it?
sir.
Yeah,
Yeah.
okay. So after that, at point B, what will be the bending moment value? At point B, what will be the value of the bending moment?
WL?
Yes, it is WL, and the variation will be linear. Okay?
Linear.
Yeah. And from B to C?
Constant.
Yes. So B to C, it is constant. And from C to D? What is the value of bending moment between C and D?
There is sudden jump to
Okay.
WL.
There is a sudden jump, but the bending moment value at C to D, whether I can draw it as a straight line like this, or like should I have to move it like this or something like that?
It won't be straight lines.
Yes, so the bending moment between point C and point D is actually 0. Okay, so it will be like this, and this magnitude is WL. Okay.
Yes, sir.
Okay. So if you have any doubts, like you can ask like how you got this WL like that. If anyone cannot understand this, then you can ask me. Up to this it is clear, right?
Yeah.
Okay. Thank you. So why I've done this actually, because here in at this section between C and D you are having bending moment to be 0, whereas between B and C you are having a constant bending moment, whereas between A and B you are having a bending moment which is linearly varying. Okay, so from this we could, within this same beam we can actually get three types of deflection curvature. Okay, here the curve will be, can anyone say what will be the curve here? What will be the curve of the deflection look like? And what is the curve of deflection here look like?
Sir, would it be parabola?
Yeah, where it will be a parabola?
A to B.
Yes, A to B it is a parabola. And from B to C, that is trivial, right? Since you
Circular.
already,
Yes, sir.
yeah, circular arc. And from C to D,
Seems like there would be a constant.
yes, constant means it's like kind of a straight line. Okay,
Yes, sir.
yeah. So up to this it is clear, right?
Yes, sir.
Yeah, so within the same beam, like we are actually getting three different curves or three different deflection curves. Okay. Yeah.
Hmm.
So now we will solve a problem. Okay. So for this beam given here, okay, based on the formula sheet which I have shared, you can actually say what will be the deflection, what will be the maximum slope and deflection. Okay. M equal to W to L. Okay, and this is point A, it's of length L, and this is point B. So how can we actually solve this? So we are going to take this same beam and we are going to actually split this beam into two different loadings, since like both we have not got any formula for a combined value of this, right? Whereas we have the formula for individual loadings of these two point loads and bending moment. Okay, so for that we are actually splitting the loading like this, plus deflection due to this. Agree? Can I do like this?
Sir, sir,
Yeah.
could you please tell me how could we do that?
Could you please tell me how cute?
How could we do that? I mean,
Okay, see, actually, this see, we have to find what is the maximum slope and deflection. Okay, yeah. From this, we could actually say the maximum slope and deflection will be at point B. Okay, why? Because see, I'm actually splitting this same beam into these two individual loads. Okay, this I can do
okay.
because I don't have a combined formula for both these things included. Whereas I have the expression for y max and theta max for these two things separately. Okay, and for all these two things, the y max will happen at B.
Huh.
So I can easily separate between these two loads like this. Okay, and then when I find the y max for this case separately, and then if I find the y max for this case separately, then I can easily add both these y max and I can,
Yeah, now got it, sir.
yeah.
Got it.
So can you say what will be the value of theta for, let's say this is the first case and let's say this is the second case. From the formula sheet, can you say what will be the value of theta b for the first case?
WL square by 2
Theta
EL.
B or theta A?
Theta b, because we want the maximum slope, right? So here you can easily say the maximum slope will be at point B, right?
Yes.
Yeah. So based on that, we are actually interested to find the slope and deflection at point B. Okay. So from the question, we can easily understand like the maximum slope or the deflection will occur at point B. Okay. So we are only interested in calculating the maximum slope. So directly from the formula sheet, you can write separately what will be the values. So it will be WL square by 2EI. Okay.
Okay, sir.
Yeah. One minute. And what is the, for example, what can I say about the sign of theta, whether it is positive or negative, and in which
That
direction? Yeah,
that would be positive, sir.
yeah. Why? Because
Anti-clockwise.
yes, since I am actually measuring this as theta b1. Okay, so this angle I am measuring. Okay, so this angle is measured in the anti-clockwise direction. Okay, in this direction.
That it is clockwise, so it should be negative.
Sorry. 1 second.
Isn't it anti-clockwise?
Sir, we may for that we measure it at A on yes.
Okay, if we measure it on A, then also it's like clockwise, right?
Yes, sir, negative.
Yeah, so it's actually negative, not positive. Okay, so maybe I can denote the arrow here. Okay, so this is the clockwise direction. Okay, or else I can write it as clockwise direction. Or if you want in terms of like what to say, sign convention, then I can write it as minus WL square by 2EI. Okay.
Okay.
In the question they might be going for clockwise or anti-clockwise direction. Okay, so based on that you can actually choose, or else if they give in terms of sign convention, mostly they won't be giving sign convention. Okay, if at all they are asking like with the sign convention, then you can go for the sign convention, like for clockwise it is negative and for anti-clockwise it is positive. Okay, yeah. So what will be YB? It will also be negative, right? Because we have seen like the downward deflection is actually negative, whereas the upward deflection is positive.
Hmm.
Yeah. So and what will be the value of YB1 separately for the first case?
WL cube upon 3EI.
Okay, WL cube upon 3I. And for example, if I mention like this, I can write it as a positive sign because I mentioned explicitly the direction. Okay. And if I am not mentioning the direction, then I can write it with sign. Understood, right? Yes?
Yes, sir.
Okay. So then what will be the value of theta b in the second case? Here I am writing, okay?
ML upon EI.
Yes. Since it is a case of pure bending, okay? It will be ml upon ei. And what will be the direction of the theta b for the second case?
Positive?
A positive,
Negative.
yeah, it will be negative because see, this can be taken to be like a loading like this, okay? So this kind of load will give me bending moment at B as M is equals to W into L. Right or wrong?
Yes.
So due to this, what happens? This beam will actually deflect in the downwards. Okay. So due to this, you will be measuring this angle only. So it will be negative, which means clockwise direction.
Okay.
Understood?
Okay, sir.
Yeah. So again, it will be a clockwise direction. And what will be the value of YB2?
ml square by 2 ei.
Yeah, it will be ml square by 2ei. And again, this will be in the downward direction. So when you add both these things, since both are clockwise direction, you can simply add, okay? There is no need for like a net slope, okay? So you can directly add theta b1 plus theta b2 and then finally you can find the maximum slope. And then for maximum deflection also, you can directly add these two values. Okay? So the final answer of theta b will be theta b1 plus theta b2. And the final value of yb will be, or the maximum slope, okay, theta max. And here it is y max will be yb1 plus yb2. Okay. With respect to sign convention alone, be careful, okay? Analyze in which side the beam or the deflection curve would be bending, okay? So based on that, you can easily find what is the value of theta b. Whether you are taking this side or this side, only you have to take the acute angle, okay?
Okay, sir.
Yeah. So can we proceed to the next problem?
Sir.
Yeah. So again, there is this question. Okay. And this is point P, A, B, C. And this is of length L. And here I am having a load of W. And let's say this length is L minus X. And let's say this length is X. So you have to find the value of X so that the deflection at B should be 0. Okay. The question is find the value of X if deflection at B is 0. Can you work out and say? First, what you will do? If you have any doubts, you can ask me. Okay.
Yes, sir. I have
Yeah.
no doubt.
Yeah.
We transfer the load to B.
Yes. So we have already seen this kind of rod questions during our SFD and BMD diagrams, right? When we are learning SFD and BMD. So similar to that, you can actually transfer the loads from D to C to A to B. So directly you transfer these loads W to A B. Okay, and say
Okay.
and say what is the load looks like for this AB section. This length is also L. So anyone?
It will be downward W at B.
Yes, it will be downward W at B, and then
And anti-clockwise movement at B with
yes, hmm,
W into L minus X.
yes, it will be anti-clockwise moment. W into L minus X. Okay, so how I have transferred actually this thing means, for example, this same W you can easily transfer it here. Okay, and then this W into X will actually cause a bending moment like this to this beam. Okay, so we have written W into L minus X. This is the very abstract thing. Okay, for example, you can also proceed by the step by step method which I have taught you earlier in the SFD and BMD class. Okay.
Hmm.
Yeah. So from this is actually similar to the question which we have already seen in the previous question, right? Same W we are having, only the moment direction is changed. Okay, so that only we are actually getting difference slope value. Okay, or the different deflection value. For example, for this loading, both for W as well as M, the bending moment, the deflection is towards the downward direction. Okay, whereas for this, one will be having a downward direction, whereas the other one will be causing an upward deflection. So can you say again? Can I again separate this, right? Excuse me. Again, I can separate it like this, right?
Yes, sir.
Yeah,
Yes, sir.
yeah. So this will be something like this, W into L minus X. So which will cause downward slope and which will cause upward slope. So this will be upward direction and this will be downward direction. Okay.
Yes, sir.
Yeah. So from this, can you find out what will be the value of Y?
Yes, sir. W
I mean,
L
sorry,
cube
what will be the value of X? Yeah. Hmm. Yeah, go on. Sorry to interrupt you.
W L cube upon 3 EI
Yeah. This, what should I have to do?
will be equal to
Yeah, will be
the
equal to,
upward.
because yeah, upward deflection.
Yes,
Yeah, since this is downward, so it can be a negative value and this will be a positive value. So when I'm writing the net deflection, which is like y1 plus y2 equal to 0, so this will be a negative value and this will be a positive value, so I can actually equate its magnitude. Okay, or else if I'm taking the sign convention, then I can write it with the sign convention and then I can go upon. Okay, so WL cube by 3I equals to what?
ml square upon 2 EI.
Yeah, ml square upon 2ai, which is here m is like w square into L minus x the whole square. Sorry, m.
Y square, sir.
Yeah, yeah, yeah. W into L minus x is m, okay, into L square divided by 2ei. So what is the value of x then?
L by 3.
Yes, it is L by 3. So from this you will get x is equals to L divided by 3. Is this clear?
Hmm.
Yeah. So I am proceeding to the next problem, okay? So for the given beam, you have to find out the support reactions, okay? What is this beam called?
Propped cantilever.
Yes, it is propped cantilever beam. And here you are having a uniformly distributed load of magnitude W newtons per meter, okay? And it is having a length L, and this is point A. You can name it as point A and B. So can you find out the support reactions from the deflection equations? First, what I have to do?
Free body diagram.
Yes. So if I draw the free body diagram, what you will be having a reaction here. I am naming it as RB, and you will be having a reaction here. I am naming it as RA, and you will be having a bending moment reaction also. Moment reaction, okay, which is MA. So this same system,
Anti-clock
yeah.
movement reaction will be anti-clockwise.
Oh, okay, fine. Okay, yeah.
Yes.
So first, can you find out what will be the value of RB? How you will do this? See, you are having two equations like the net load, okay, is RA plus RB equal to W into L. This is one equation you are having, but here both RA and RB are unknowns, okay? So you are going for deflection equation, okay? So for the deflection equation, what I can do, I can split this system into two things. I have given based on the formula sheet, you can actually predict, okay? This is one system, okay, and this is the other system, right? So from this you can find out easily what is the value of RB, right? So what will be the deflection for or the maximum deflection, and where it will happen for this beam? The maximum deflection occurs at point B, right? And what is its value?
WL is to 4 upon 8 EI.
Yeah. And the deflection, whether it is downward or upward?
Downward.
Yeah. So let's say this as y1 and let's say this as y2, okay? And since it is hinged here, okay, we can say y1 plus y2 equals to 0, okay? So what will be the value of y1? As someone pointed out, it is like minus wl divided by 8ei. And what will be the value of y2? Since it is in the upward direction, I am giving a positive sign, okay? And it will be rb l cube divided by 3ei. Is it?
Yes, sir.
Yeah. And from this, what RB value are you getting? What is
3
the?
W
Yeah, 3W.
3 WL by 8.
Yes. So it is 3WL by 8 and the direction is upwards. Okay. And from this, what is the value of RA? You can easily find out, right? WL minus 3WL by 8, which will be 5WL by 8. Okay. And from this, you can easily find out the moment. Okay. So it will be like 3, for example, if I find out the moment at A, like RB into L and this W into L acting at its center. Okay. So, for example, if I am taking the anti-clockwise moments as positive, okay, it will be something like this: 3WL by 8, which is nothing but RB, okay, into L minus WL into L by 2, which is a clockwise moment, okay, which is equals to the net moment, okay. So it will be 3WL square by 8 minus WL square by 2, which is equals to MA. And finally, what is the value of MA?
Minus WL square by 8.
Yeah, minus WL square by 8. And what is this minus signifies? It signifies like it is in the opposite direction. Okay, so I can write minus WL square by 8, small w, okay, in the this direction. Okay, in the anti-clockwise direction. So this problem is clear, right? How we are calculating the support reactions from the deflection equations. Okay, can I proceed to the next problem?
Sir,
Yeah.
here if we try to find reactions by regular method at point RB, then it is showing some different value.
By which method?
Means by doing summation of moment at point A is equal to 0.
Summation of moment at point A equals to 0 for finding out the value of MA.
RB, for finding RB.
No, no. Actually, you can't give the moment summation at A equals to 0, right? Because there is some concentrated reaction moment which is acting at point A. So the first thing which you have to do is like you have to find out the value of RB by using the deflection equation. And then only you can find out the value of MA by how you are finding out this value of MA is by calculating the net moment on the beam, which is the opposite value of the net moment will be given as the reaction.
Okay, so point A is fixed and not hinged. That's why we
Yes,
can't do
yes,
that.
point A is fixed, so you can't actually use summation MA equals to 0. Whereas for at point B, you can use summation NB equals to 0. Okay, only for hinged supports like the net moment is equal to 0. Okay,
Okay, sir.
here also you can use summation MA means what it actually means is like you are actually equating the net moment. Okay, which is a I mean you have to use this MA value also. Okay, so but if, at the start I don't know what is the value of MA, so I can't be writing like summation MA equals to 0 and then having like MA plus for example if I'm taking in some direction, for example like I am taking the anti-clockwise direction itself, let's imagine. Okay, so MA is in the anti-clockwise direction means in this direction which we have already assumed. Okay, and what will be the WL? It will be W into L by 2, and this causes a moment in the clockwise direction. And then plus RB, you know what is the the direction of RB alone. Okay, and it causes a moment in the anti-clockwise direction into L equals to 0. Like this you can do, which means you are actually taking the moment component, the reaction moment at A, and then you can do this summation MA equals to 0.
Yes, sir.
Yeah, which means here in this case you are actually doing like net moment equals to 0. That is the thing which you are actually doing here. So that's the thing we have done here also. but you can't actually write summation ma for only for hinged support. You can write like this: summation mb equals to 0, and then I can balance all the what to say, vertical forces. Understood?
Yes.
Yeah. So now let's proceed with a different problem. Okay. You have a cantilever beam, and you have a spring which is attached to this cantilever beam, and I need you to find the value of the deflection. Okay. Let's say this as w, and this as point b, and this as point a, and its length is l, and this as spring constant k. Okay. So can you draw this free body diagram and say like how can you actually find the, or what is the relation between these things? You are having a vertical shear force which is acting downwards at point B. Okay. And due to this, what happens? The spring gets compressed, right?
Yes, sir.
Yeah. So due to this compression, what will happen? It exerts,
Upward force.
yeah, it exerts an upward force on the beam. Okay, and I am naming this force as the spring force, or the reaction due to the spring RS. Okay, and this, and how much will be the force which is acting on the spring?
RS.
Yes, it will be same RS, because this spring only exerts a force which is RS, and an equal and opposite force will be exerted on the spring. Okay. So if I consider the spring alone as the separate entity, then it will have a downward force of magnitude Rs. Okay. So due to W, I am taking the deflection as y1. Okay. And due to this Rs, I am taking the deflection as y2. Okay. And this combined deflection will be equal to how much?
K delta?
Yes. It will be not k delta. I mean, actually, I have said I have not equated the forces. Okay, this combined deflection, for example, y1 plus y2 is equals to delta of spring. Okay, k delta means it signifies like you are actually mentioning about the force term, spring force, which
Ah,
is
yes.
nothing but Rs. Okay,
Yes, sir.
so yeah, so this is the compatibility equation which you are currently going to work on. First you have to find out the, see, for solving these kinds of problems, first you have to find draw the free body diagram, and then you have to find out the relation between the deflections. Okay, and then based on this relation you can actually from the formula sheet you can actually write down all the deflection formulae, and then you can find out what is the reaction force. Okay, so here I need to find out what is the value of Rs. Can you find what is the value of Rs here? What is actually y1?
WL cube upon 3EI.
Yes. So here, since like we are dealing with positive and negative at the same time, okay, or the upward forces, I mean upward deflection and the downward deflection at the same time, it is advisable to write with sign convention. Okay, so it will be minus w,
Minus B.
yeah, WL cube by 3EI. Then what will be the value of y2? It will be same, Rs L cube divided by 3EI, which is equals to, what is the value of delta? Here I have written, right, delta is equals to Rs by K. Okay, and here I have to write it with the sign convention, since like the spring is getting compressed in the downward direction. Okay. So what will be the value of Rs? For example, if I'm taking Rs to one side, Rs into 1 by k plus L cube divided by 3EI, okay, which is equals to WL cube divided by 3EI. From this, I can write Rs as like multiplying Rs is equals to 3EI plus KL cube divided by K3KEI, which is equals to WL cube divided by 3EI. So both sides 3EI gets cancelled and you will be having WL cube divided by K into, for example, Rs I need, right? 3A gets cancelled, so K goes upwards and you won't be having this. It will be. Are you working out simultaneously?
Yes, sir.
Yes,
Yeah.
sir.
Yeah. So you are getting this answer, right?
Yes, sir.
Okay. So, and if they ask what is the deflection of the spring also, then you can easily find out. Delta is equals to Rs by K. Okay. Up to this it is clear. Can I proceed to the next problem or should I have to wait? Can you say how many people are there in this meeting?
12.
9 people. Okay. So let's proceed to the next problem, okay? So again here, determine the spring force, okay? You are having a system like this. In between you are having a spring, okay? And this is point A, this is L, this is L, and here you are having a force W. This is point B and point C, okay? And you are having a spring constant K. For this, can anyone say what is the compatibility condition? You can name this member as 1 and you can name this member as 2, okay? So due to this type of loading, what happens? See, you are having a concentrated point load at point B. Okay. So due to this, what happens? This member 1, okay, it will deflect something like this. Okay. And you are naming this deflection as YB1. Okay. And this deflection, since you are having another one beam here, okay, what will happen? See, due to this, this spring gets compressed, right?
It will cause equal deflection.
Yeah, equal deflection, yes. See, but you are having what to say, a beam at the bottom which is attached to this same spring. Okay, for example, due to this deflection it will cause a reaction like this, Rs, for the beam. Okay, for example, if I draw the free body diagram of the beam, it will be something like this. Okay, whereas for
Okay.
this, yeah, whereas for the spring it will be something like a compression. Okay, but this rs, okay, it should be transmitted here also, right?
But sir, that compression won't be measurable, right, sir?
Yes, yes, this compression won't be measurable, but we can actually find
But
out some kind of what to say, a relation between the deflection terms, and then you can arrive at the final expression of this spring force rs.
okay, sir. Thank you,
Yeah,
sir.
that is the motive behind all these things. Okay, so up to this it is clear, right, what I have drawn. For example, for this cantilever beam for 1, okay, it will be w minus rs, whereas for this spring force the same rs spring force it will be transferred, whereas for this beam 2, okay, what will be the force which will be acting on beam 2?
Rs.
Rs, yes, in the downward direction. Okay, so from this, can you arrive some kind of a compatibility equation or a relation between one, the spring force, and the beam 2?
So the direction of Rs at lower end should be upward. No?
What? What you said? Can you please repeat it? You said something related to RS, right?
Hello, sir.
Yes.
I am asking the
Hmm.
direction of spring force Rs
Yes.
at from lower end should be in upward direction.
Yes. Here you are saying, right?
Yes, sir.
Yeah, it should be in upward direction. Yes. So can you find out the relation? Have you found out the relation? See, for example, this is the total amount of deflection for beam 1, okay, which I denote it as YB of 1, okay. And here you are actually getting spring deflection also. And here also it is deflecting downwards, okay. Here I am naming this as YB2. So whether it is like YB of 1, which is equals to delta S plus YB of 2, or else like, yeah, we have named this as point C, right? Is it something like this or not? Yes, see, this beam actually bent by an amount YB1, okay. The same amount, this combined action of this spring force act as well as this beam 2 should be bent, okay. That is the compatibility condition which we are actually having here. Okay, I can't have a different deflection of let's say delta S and YC2 which is independent of YB1. Okay, at what value of YB1 this beam 1 is bending, the same amount of deflection this combined delta S plus YB2 should be producing.
Sir, but deflection of beam 1 is independent. So how it is going equal?
No, see, actually this beam 1 is bent by a distance of YB1, right?
Yes, sir.
Yeah, so and also like you are having a bending of beam 2 also, which is due to rs, and also you are having a compression of the spring due to rs, okay.
Yes.
Yeah, so when this beam is bent like this, then ultimately this what to say, this spring force as well as this combined thing will also be bent by this same y2 distance, I mean YB1 distance, so that only you will be having this deflection as YB1. Otherwise, you won't be having. This is YB1, okay. And let's say, suppose this total compression is delta S, okay. and let's say this total compression of this beam 2 is yc2. Okay, this yb1 should be equal to this total deflection of delta s plus yc2. Otherwise you won't be see, for example, you won't you can see this k as some independent quantity, because the same force rs is acting on both the spring as well as this beam 2. Understood or not? Hello?
Yes, sir.
Yeah, you can think about this also. Okay.
Yes.
Yeah, see, when you are thinking about this as a single entity, only then you can imagine this. Okay, this first beam is actually bent down by a distance, or it is deflected by a distance of yb. Okay, let's say this as 10 mm. Okay, and this spring force is getting deflected by 5 mm, and then this thing will also get deflected by 5 mm. Only then you can have this total deflection as same 10 mm. Okay, that's the thing I'm saying. You can't have a deflection, say for example, like this to be like 3 mm, and you can't say like yb1 is greater than this combined action of delta c plus yc2. Okay, that is not the case. That's the
So
thing I'm saying here.
means by whatever amount beam 1 is going to go downside, that
Yes,
will be taken care by that spring and
as well as
second.
this beam b2.
Okay, sir.
Okay, so maybe if you imagine some values, then you can actually arrive at this conclusion. Okay, and can you find out what is the expression of yb1?
RS minus W.
Yeah. So here I am taking the up, like the downward force, okay, is equals to this total downward force. Since all these things are in the downward direction, so I am just equating the magnitude alone. Okay. So here W minus RS into L cube into 3EI. Okay. Why I have given minus rs means like it is in the upward direction. Okay, here I am taking all the downward deflection as positive, and then this as rs by k, and here it will be rs L cube divided by 3ei. Okay, you can also take the upward direction as positive and downward direction as negative, and then finally what will happen, rs will be positive and all the w's will be negative. Okay, so can you find out what is the value of rs from this?
WKL cube by 2KL cube plus 3EI.
Oh, is it correct? Okay, let's WL cube divided by 3EI minus RS L cube divided by 3EI, which is equals to RS L cube divided by 3EI plus RS by K. Okay, when I shift this to all the RS to right hand side, then RS L cube divided by 2 RS L cube, yeah, 2 RS L cube divided by 3EI plus rs divided by k will be equals to wl cube divided by 3ei. Okay, so from this here I am working it out, all the remaining things. Yeah, so it will be rs into 2 l cube divided by 3ei plus 1 by k will be equal to wl cube divided by 3ei. So here I am imagining this spring constant value equals to EI divided by 2L cube for simplicity, okay, so that the terms cancel out and you will be getting a nice expression for RS, okay. So 2L cube divided by 3EI. When I substitute this, what will happen? It will be 2L cube divided by EI, right? Which is equals to WL cube divided by 3EI. So EI terms will get cancelled and L cube terms will get cancelled, and you will be having RS into 2 by 3 plus 2, which is equals to W by 3. Is it correct? So RS will be equal to 2 plus 6, 8 by 3 W by 3. So finally you will be getting RS equals to W by 8. Okay?
Okay.
Yeah. So if you want to copy, you can copy, otherwise I will move to the next problem.
1 minute, sir.
Yeah. See, for simplicity, I have taken this k value to be EI by 2L cube so that it will get cancelled. Okay.
Means k value is need not to be that one. No?
Yeah, k value need not to be this value. For simplicity, in order to get like W in terms of W, I have given k value equals to EI by 2L cube. Okay.
Yes.
Yeah. Shall I proceed to the next problem? Okay, I'm going to the next problem. Okay. This problem is very important. Okay. Can you find out what is the deflection and slope at C? In order to proceed this problem, first can you draw the shear force diagram and bending moment diagram? What is the shear force diagram and what is the bending moment diagram?
Rectangle for A to B.
Okay, and after that?
Nothing.
Yeah, okay. For bending moment?
Elliptical.
Yes?
Linear.
Linear, yeah.
Sir, how could it be linear? Could you please tell me? Didn't get it.
Okay, see, for example, here you are having a reaction like this, right? W.
Huh.
Okay, and then you will be having a moment reaction. For example, if this is the case, then you will be having a moment reaction at MA equals to W into L by 2. Okay,
Huh.
so when you are having a section here, okay, then what you will be having? You will be having the bending moment equation for the section AB equals to, it will be W into X, right?
Hmm.
So the variation of the section between AB, it is a linear.
Okay, sir. Got
Okay.
it. Got
Yeah. And after this, it will be 0.
it. 0. Hmm.
Yeah. So what will be the radius of curvature then, or what will be the deflection curve up to A to B? It will be a parabola. Okay.
Hmm.
Okay, let's imagine this as the parabola. Okay, up to I will. Yeah, up to A to B it will be a parabola, and after that what it will be?
Straight line.
Yes. So it will be a straight line. So, for example, you want the value of the slope at C and as well as the deflection at C. Okay. So this section I am demarcating like with a bright dot. So this is actually parabola and this is a straight line. So what will be the, for example, if I have the slope at, if I know the slope at point B, okay, let's say this as the slope at point B. And what will be the slope at point C? What will be the relation between the slope at point B and what will be the relation between the slope at point C? Anyone? See, this is B. Okay, you from A to B, it is a parabola, and from B to C, it is a straight line. Okay, so at B, I am having a slope value something like theta B. Okay, and then from here on, okay, this is let's say this is YB. Okay, and here on I am having a straight line like this. So what will be the slope at point C? For example, if I draw a tangent to this, will it won't be the same straight line?
Yes, sir, same.
So what will be the value of theta C? Whether it will be equal to theta B?
Yes, sir.
Yes, sir.
Yeah. So that's the point I want to make here. Okay. So theta B equals to theta C in this case. Okay. And what can you say about YC? Up to here, you know the deflection is YB. Okay. But this is the total deflection YC, and you know this angle as theta B, right? So can you correlate this? For let's say, let's imagine this as y1 and this as y2. Y1 is equals to what? YB, right?
Yes, sir.
Yeah, y1, this is the distance of y1 and this will be the distance of y2. Okay, so y1 is equals to yb, and how can I find out y2? Let's suppose this is theta b. Tan of theta b I can write, right?
Yes, sir.
Yeah, tan of theta b equals to what?
Y2 by L by 2.
Yes, y2 by L by 2. So you need y2. So y2 is equals to tan of theta b into L by 2. Okay. And for small angles, what will be the value of tan of theta b?
Theta B.
Yes, it will be theta b into L by 2. So therefore, yc is equals to yb plus y2. Okay. So for this, what you have to find out then? You have to find out the value of yb, and then you have to find out what is the value of theta b, and then you can substitute the things here, and then you can find out what is the value of theta c and yc. Okay. This is the method. Okay. Is everything clear?
Yes, sir.
So how you find out what will be the value of theta b then?
WL square upon 2EI.
Yes, it will be wl square upon 2ea. And what will be the value of L here?
By 2. L by 2.
It will be L by 2 since I am taking only this portion. Okay, this portion as the cantilever beam. Okay, and the length will be L by 2. Okay, W L by 2 the whole square upon 2EI. So it will be W L square by 8EI. And what will be the direction? It is clockwise. Okay. And this is equals to theta c. Okay. And how to find out the value of yc? It will be yb. What is yb?
WL cube by 3i.
Yes. So w here L is L by 2. Okay. So w L by 2 the whole cube divided by 3ei plus theta b. Theta b is w L square divided by 8ei into L by 2. Okay. Then you will get what will be the value of yc. How much you are getting yc? What is the value of yc?
5W L cube upon 40
Yes, 5w L cube upon 48 ei in the downward direction. Okay. So this is the method to solve for yc or theta c when the point load at when a load is acting at the midspan. Okay, or at any other length. Okay, is this fine?
Yes, sir.
Yeah, and this thing you can use only when you are having the shear force, I mean the bending moment here as a straight line. Otherwise, you can't use like this. Okay, based on this straight line concept only, we have been equating like theta b equal to theta c, and then like y2 is equals to tan of theta b2 into L by 2. Otherwise, you can't use. Okay, so I'm giving you a question here. Okay, determine, like for example, for this particular loading. Okay, this is 3L by 4 and this is L by 4. Determine P by Q ratio when theta c equals to 0. This is the first one. Okay, and determine P by Q ratio when yc equals to 0. Can you do it?
What is C, sir?
Okay, this is B and this is C. How you will proceed with this problem? Anyone? Or shall I say? Or if anyone wants to make a try, you can try. Shall I say then? Okay. See, you are having a beam like this. Okay, they want you to determine the ratio of P by Q when theta c is equals to 0 and the ratio of P by Q when yc is equals to 0. So the first step what you have to do is like you have to split this loading into two individual loadings. Okay, let's name this as 1 and let's name this as 2. Okay, this is P and this is Q. And the length is, here it is L, here it is 3L by 4 and here it is L by 4, and I am naming this as 2. So now can you find out? So what you will do, you will equate y1 equals to y2, right? right or not?
Yes, sir.
Yeah. So what will be for the first thing? It will be, for example, let's say like we are proceeding with theta c equals to 0. Okay. For the first case, what will be the value of theta 1? It is PL square
3
by
is 3,
2E.
3i.
Yeah. And here, what will be the value of theta 2? Q L square by 2EI. Whether I should change anything or I should like leave it as it is.
L to 3L by 4.
Yes. So that is the major change I have to do here. So here, similar to the last problem which we saw, right? Only difference is like here Q is at a distance of 3L by 4. And after that, you can see like the bending moment value is actually 0. Okay. So you can write theta 2, I mean theta c equals to theta b here, and then theta b equals to q into 3L by 4, the whole square divided by 2EI. Understood? 9QL square divided by 32EI. Okay. So when I equate these two things, because one is in the, I mean, like for example, if it deflects like this, right? One is in the anti-clockwise direction, and another one deflects like this, and this is in the clockwise direction. Okay. So it will be PL square by 2EI equating it to 9QL square divided by 32EI. And what will be the ratio of P by Q then? It will be 16, so 9 by 16. Okay. In similar line, can you determine what will be the ratio of P by Q when YC equals to 0? So when YC equals to
Yes, sir.
0, yeah. What is Y1? It will be PL cube divided by 3EI. And what will be Y2? Any modification I have to make to find what will be the value of Y2. Y2 is nothing but the deflection at point C for the second case. So what I should write? Here maybe I will write YC2, okay? Can anyone tell the formula how to find out what is the say deflection at point C for the second case?
YB plus
Okay,
theta B into L by 4.
theta b into L by 4, yes. Thanks. Okay, so what is YB for the second case? Q into what is the length I should take here? 3L by 4, right? WL cube 3L by 4 divided by 3EI plus theta B is nothing but 9QL square divided by 32EI into L by 4. And what is the value of YB2 you are getting? I mean YC2. What is the final answer you are getting? Anyone? Okay. So it will be 27 by 128 into QL cube divided by EI. Okay. So after this, I have to equate yc of 1 with yc of 2. Okay. That part I am doing it here. So yc of 1 is nothing but PL cube divided by 3EI, which is equals to 27 divided by 128 QL cube divided by EI. So what is the P by EQ ratio which you are getting? 81 divided by 128. Okay. Shall I proceed to the next problem?
1 minute, sir.
Yeah. If anyone has any doubts, you can ask, please.
Hello.
Yes.
Sorry, the link that Priyanka sent me for Google Drive, it's not working actually.
Okay. For the thing Google Drive formula sheet you are asking.
Yes.
Okay, 1 minute. I am sharing the link again. Okay.
Yes, okay.
Yeah. So now shall we proceed to the next problem?
Yes, sir.
Yeah. So before proceeding to the next problem, I want to say about Maxwell's reciprocal theorem. Okay. So here we have solved remember this problem also, like you are having a load at point B, okay, and then you are calculating the deflection at point C, okay. So in the next problem what we will do is like we will have a load at point B, okay, and we will be calculating the deflection at point B. It is L by 2, L by 2, this is point C, B, A, okay. So you want to find out what is the slope and deflection. Sorry, not load at point B, load at point C. Can you find what is the deflection at point B? Which is at a distance of half. See, for this, what we have to do is like we have to take the same system. Okay. Only thing you have to translate this load to point B. How you will translate the load from point C to point B?
Equal and opposite W at B.
Yes. So equal and opposite W at B, and then this W and this W will cause a bending moment, right? So I'm writing this as like this. This is W, and then I'm having a moment which is equals to W into L by 2. Is it correct or not? Okay. So for this, can I now can I find out what is the value of theta b and yb?
Yes, sir.
Yeah. So what I will do again, I will, since there are two different loadings, I will again split this into W and then plus this thing WL by 2. Okay. So this has 1 and this has 2. Then can you find out what will be theta b? It will be theta b1 plus theta b2, right? So what will be the value of theta b1? WL square by 2EI. Okay. So what is the value of L? It will be L by 2. Okay. WL square L by 2 the whole square divided by 2EI plus what will be the value of theta b2? It will be ML by EI. So M is nothing but WL by 2 into L is nothing but L by 2 divided by EI. Okay. So which will be nothing but WL square divided by 480i plus WL square divided by 4EI, which will be nothing but 3 by 8 WL square divided by EI. And since both of these things is giving in the same direction, okay, both these things will bend downwards, right? So the slopes are in the same direction or the clockwise direction. So we have added both these things. Okay. And what will be the value of YB? It will be YB1 plus YB2. Okay. What is the value of YB1?
WL cube by 3i.
Yes. So instead of L, I should write L by 2. Okay. 3i plus what is the value of YB2? It will be W or ML square by 2EI, right? So M is here WL2 divided by L is L by 2 square divided by 2EI. Okay. So when I add both these things, it will be WL cube divided by 2 cube 8, 24 EI plus WL cube divided by 2 square 8, 16 EI. So it will be 5 WL cube divided by 48 EI and in the downward direction. So can you, up to this it is clear, right? How we have found out theta b and yb? So can you note any similarities between this problem and this problem? For example, here I have taken load at point C, okay, and I have calculated the deflection and slope at point B, okay. And here I have taken the load at point B and then I have calculated the deflection and slope at point C, okay. So from this, the slope at point B and point C is like WL square by, I mean the slope at point C is nothing but WL square by 8EI. Whereas here the deflection is 5WL cube by 48EI. Okay. When the load is acting at point B, I have calculated the deflection at point C. Okay. Whereas here the load is acting at point C, whereas the deflection I am calculating at point B, and still I am getting the same value of deflection. Okay. So from this, the reciprocity theorem comes. Okay, Maxwell's reciprocity theorem. Okay, Maxwell's reciprocal theorem. And what it states is like, okay, you have similar beams. Okay, this theorem is valid only for this theorem is valid for any type of beams, but both beams should be identical. Okay, for example, I have a beam like this and I have a load, say for example WA at point A, and then I have a point B, and I have a deflection curve like this. Okay, and due to this deflection, I am naming this as YB equals to YBA. YBA means due to load at A. Okay, what is the deflection? I am finding out the deflection at A, and then I have an identical beam. Okay, and the only thing here is like the load is acting at point B, whereas I need the deflection at point A. Okay, and this is nothing but YAB. Okay, YA equals to YAB, where YAB is nothing but load acting at B, or due to load at B, I am finding out the deflection at A. Sorry, here it should be deflection at B. Okay, so based on the what Maxwell reciprocal theorem states, like WA into YAB equals to WB into YBA. Okay, and when you have W as equal, then what it will happen? YAB equals to YBA, if and only if WA equals to WB. Okay, so this is the thing which we have seen in the previous problem. Okay, for example, I have a load at C. Here I have load at point C, whereas I have calculated the deflection at point B. Okay, same W, and I got the deflection as 5WL cube by 48 EA. Then if I have the same load which is acting at point B, and if I need the deflection at point C, then directly I can write it is 5WL cube by 48 EI. Okay, that is the thing which we have seen here. Okay, so this Maxwell reciprocal theorem is clear, right, to everyone?
Yes, sir. And this is only for deflection and not for slope, no?
For slope, like you need to have concentrated moment. Okay, for example, MA theta AB equals to MB into theta BA. Okay, this is the relation for moment.
Is this also Maxwell's?
Yes, this is also Maxwell reciprocal theorem. Okay, for example, here, if you are finding out what is the theta B value, it is 3 by 8 WL square by EI, right?
Yes.
Yeah, whereas for there also it is like
It was different.
no, different, WL square by 88. So for only for, see, when load alone is acting, then you can equate only deflection. Okay, whereas like moment alone is acting, then you can equate it for like slope, not for deflection. For example, for moment, if I have to give you the example, then it will be something similar to this. Instead of load, I will be replacing it by a moment. Okay, this is A, this is B, and this is B. Okay, here I can't equate the deflection. Here only thing I can equate is like slope I can equate. Okay, if I have the same n value, then what it will turn out, theta AB equals to theta BA, meaning like the slope at A due to moment at B equals to the slope at B due to the moment at A. Okay, this is the convention which we are following. Okay, from this convention you can actually generalize it to theta also. Is it clear?
Yes, sir.
Yeah. 1 minute. So I think time is up. Actually, I thought of completing with a moment area method, and then Castigliano's theorem is there, and strain energy is there. Okay. So I think we will be meeting January 16 we can meet, then January 23 we can meet, and then after that Jan 30 I think we can meet. So three classes are there, right, for us. So in the next class, we will be seeing about moment area method and Castigliano's theorem and strain energy. Then January 23, I have to complete torsion. And then January 30, I have to complete principal stresses and strains. So if possible, if everyone wish to come for this any extra class, then we can find a common time and then we will have some extra class for maybe principal stress and strains, and as well as thin cylinders and thin spheres, and then theory of columns. Okay, those who are interested can attend those. Okay.
Yes, sir.
Yeah. So up to this it is clear,
Okay.
right?
Yeah.
Yes, sir.
Yeah.
Yes.
If see if I want to change anything with respect to problem solving, or if I'm going slow or fast, like you can say anything. Any feedback you want to give, then you can give. Otherwise, feel free to leave. Okay.
Sir, 1 minute, sir.
Yeah.
Okay. From that, we know one previous problem. I have to ask about the bending moment diagram.
Okay. 1 minute.
From today's session only.
From today's session only. Okay. Which thing you want to ask? This one or this one? Can you exactly specify the problem?
After springs,
Spring. This spring sum we have attempted, and the other spring sum is like this one, right?
after this.
After this.
Yes, sir.
Yeah, this is the problem which you're asking.
No, sir. After this.
After this is like this one.
Yes, sir.
Yeah.
Here, BMD is not inverted.
Okay, you are saying like the value should be negative.
I mean, it should be negative triangle.
Okay, for example, this is WL by 2 in the clockwise direction, then this is anti-clockwise direction. No, it's positive, right? For example, we are actually taking left clockwise as positive and right anti-clockwise as positive. So here MA is actually anti-clockwise. Yes. So BMD will be like this. Okay. This is the thing you want to say.
Yes, we have done this for simply supported beams, but I think you were telling that sign convention was valid only for simply supported and cantilever offers different sign convention. No?
No. See, for example, here the bending moment diagram is always drawn by this sign convention: left clockwise, right anti-clockwise. Okay, so when I have a section here, and if I see this WL by 2, okay, here what is this bending moment? It is on the left hand side, right? Left hand side of my cross section AB.
Yes.
Okay, and in which direction it is? Actually, it is anti-clockwise direction, so it is
Yes.
negative. Okay, this is
Yes.
for bending moment sign
Yes.
convention alone. For example, if I'm going for like finding out the moment reaction itself, for example, how I came to the conclusion like it is acting in anti-clockwise direction of magnitude WL by 2, then I will go for this clockwise moments, anti-clockwise moments, something like that. For like for example, it is WL by 2 in the clockwise direction, so there should be some anti-clockwise moment which nullifies this WL by 2, because I'm having a fixed beam or the fixed support at point A.
Okay, sir. Means this BMD is correct.
Yeah, the BMD which I have drawn in the downward is correct, whereas the upward is wrong. Okay, since I thought it is a triangle, like I have drawn it in the positive direction, but it is actually in the negative direction. Since left, we are always following the sign convention for bending moment as left clockwise and right anti-clockwise. Okay.
Okay, sir.
Yeah. See, this left clockwise and right anti-clockwise is applied for every kind of beam.
Left clockwise positive.
Yeah, left clockwise means positive, right anti-clockwise is also positive.
Okay.
Yeah. Shall you wind up the class then?
Yes, sir. And you were telling about that last time extra classes. What will be that timings?
Yes, maybe around after January 23, we will decide one common time and then we will proceed. Okay. Maybe
Okay, sir.
on weekends we will try to have, okay, 1 hour or maximum 2 hours we will try to have, and we will finish it off. Okay.
Okay, sir.
Yeah. So thank you everyone.
Thank you, sir.
Thank you.
Thank you, sir. Thank you. Thank you.
I have big problem in this topic.
Which problem?
Actually, today I faced big problem in this topic. So few things I understood, but few I mean during class like all seems like unknown to me.
Okay. Okay. So which problems you haven't understood well?
Uh, that's spring
Your voice is actually breaking when you are talking.
spring.
Spring problem. Okay. Okay. Maybe you go through my lecture again. Okay. I will
I
upload the
I would
lecture.
like to,
Yeah.
yeah, and I like studied by, so extra what kind of like note about like
Okay. See, maybe you
which
can
I
solve
follow
all the gate
will get.
previous year's questions. Okay. One thing I would suggest is like you can, if you are solving, if you are able to solve all the previous year's questions, then that is like around 70 percentage of the work is being done. Okay. When you are able to solve. Okay. And
Okay,
then you can actually solve the questions which are available from any what to say the gate coaching centers. Okay, if you are able to solve some basic problems, okay, not very difficult problems, some basic problems, if you are able to solve, then that's also fine.
thank you, sir.
Yeah.
Thanks a lot.
Yeah.
Sir,
Yes.
I have small doubts, sir.
Yes.
Sir, in every year means we are getting new questions. Then how previous year solving is going to means
Yes,
effective?
actually, see, for example, every time in GATE exam, mostly, for example, if the question paper is in medium level, okay, not too tough or not too easy, then, for example, if you are able to solve all the GATE problems, then easily you can score around 60 marks. Okay?
Okay, sir.
Yeah, easily you can score 60 marks only by attending for 70 questions. I mean, 70 marks. uh, at that time, at that moment, you can easily skip which are the tough problems. You can easily skip those tough problems, and only if you attempt all 70 marks for the entire 3 hours, then you can easily score 60 marks, because you are attending only for 70 marks, right? Then the chances of errors or careless mistakes goes down. Okay. But if you want to try for around 90 marks or above 80 or above 75, okay, then you have to solve different questions which are available from the coaching institutes.
Okay, sir.
Yeah, and then you have to take test series which are given by the coaching institutes. Only then you can go for. Only then you will be able to solve the different questions which are being asked in the gate problems or gate exam. Okay.
Okay, sir. Thank you.
Yeah, mostly like scoring above 50 is very easy when you are able to attempt only for 60, 70 marks, and then easily you can score 50 marks. Yeah.
Okay, sir.
So what is the
Yes.
No, sir,
so
thank you,
what
sir.
what is the
Thank you,
cutoff
thank you.
marks for top IITs and GATE?
The top IITs, I can't be very sure about the mark, because mark actually varies from year to year. Okay, maybe on
Approx.
an approximately I can say like above 70 you can get IITs. Okay, above 70 you can get
Okay, sir.
IITs, whereas top IITs like IIT Madras, IIT Bombay, then IIC Bangalore, then you have to score above 75 also.
Okay, sir.
Yeah. And the rank should be around less than 1500, I think so.
Right, sir.
Yeah,
Okay.
and
Thank
also
you.
it depends on the branch which you are interested. For example, if you want thermal, then you need to have very high rank, like that. Okay.
Okay, sir.
Yeah.
So
Thank you,
in
sir.
mechanical also we have to decide, we have to like choose thermal design,
Yes,
etc.
yes, yes. Thermal design, manufacturing, then industrial engineering.
Okay.
Yeah.
That means by choosing industrial engineering, we become industrial engineer.
Uh, Most probably. Actually, see, the placement scenario at, for example, wait 1 minute, I will stop the recording and then I will.